This is question 3 of assignment 3, and there are two parts to it. So in part A, it wants us to prove that two disjoint sets, A and B, which are countably infinite, the union of these two sets, A and B, would be countably infinite as well. So it wants us to prove that in part A. And in part B, it wants us to prove that the set of rational numbers, R minus Q, is uncountable. And we may use two facts without proof. The first of which is that the set of irrational numbers, R minus Q, is infinite. And secondly, the set of real numbers, R, is uncountable, right? So let's start with part A. We know that the set A is infinite, is countably infinite, right? Same thing with B. And because it's disjoint, the intersect of A and B would only have the null element, right? So if we let the union of the sets A and B be C, and C can be represented in set builder notation as this. Right? And then we define a function f that maps C to the set of natural numbers such that f of x would be equivalent to the even natural numbers if x is from the set A, and f of x would be equivalent to odd natural numbers if x is from the set B, right? Now, this implies that for all elements C in the set C, there exists an element M in the set of natural numbers such that M would be equivalent to 2C if C is also from the set of A, and M would be 2C minus 1 if C is from set B. Thus, we have shown that F is injective or one-to-one. Now, we can also see from the function f that for all values of m in n, there exists a value c in C such that exists in set of natural numbers. Oops. Let's see. Right? So for all elements M in the set of natural numbers, there would exist some value C in the set C such that because M is equivalent to f of x, M would have a value that is equivalent to 2C or 2C minus 1, where C is in the set of natural numbers and C is the element in the set C. Thus, F is surjective because all the elements in the set of natural numbers are mapped onto the set C. Are mapped back onto set C, so F is surjective, and thus F is bijective, and that means that A union B is also countably infinite. Okay, that's part A. Now for part B, it wants us to prove that set of rational numbers is uncountable. Okay, so we know that R, the set of irrational numbers, is infinite, and that means two things. Either R minus Q is countably infinite, or R minus Q is uncountable. Right? R is uncountable. Suppose that R minus Q is countably infinite, right? Just for sake of argument. Then that would imply that R is countably infinite because R would just be equivalent to the union of the sets R minus Q and Q, because we know also that Q is uncountably infinite. And in part A, we've showed that the union of two countably infinite sets would give a countably infinite set as well, right? Thus, if we know for sure that Q is countably infinite, then R minus Q cannot be countably infinite, because if it's countably infinite, then R would be countably infinite. But we know R is uncountable. So that means one of either q or r minus q is uncountable. But we know q is countably infinite. So then r minus q must be uncountable.